Why do people go bald?
Why are baboons' bums red?
What's a light year? Why do leaves go brown in the autumn? Why do monkeys like bananas? Why do some things glow in the dark? Why do animals not understand you? Why do my receipts fade after a year?
Don't know the answer? Ask the Naked Scientists.
Hello, welcome to this week's edition of Ask the Naked Scientists with Dave Ansell and with me, Matt Jamison. Let's get naked with the scientists, and Dr. Dave is here. Good evening, sir.
Good evening.
It's nice to have you with us as we go straight in to a question on caffeine. Andrew in Cambridge has been on the phone. Good evening to you, Andrew. He says, how do you make decaf coffee, and where does the caffeine go?
Okay, caffeine's a molecule. It's a chemical, basically. It's in the coffee beans. You want some way of getting it out of the coffee beans. So basically that involves dissolving it out. What they normally do is dissolve it out with some kind of solvent, which it dissolves well in, and then filter that solvent because caffeine will stick to sort of carbon filters like a coffee filter. And then they've got a water with a load of everything that's in coffee apart from the caffeine. They then boil some more beans in that solvent, and so because you've got lots of everything else in there, the caffeine can get out, because everything else is in solution, it can't get out as well because there's too much dissolved in there already. So the caffeine comes out, and you filter the water again, take the caffeine out, put the solvent out, and put it back in again. They've used lots of different solvents. They used to use more dodgy ones, like things like benzene. These days they do a lot of it with high pressure carbon dioxide. So you get carbon dioxide, get it really hot, put it under really high pressure, and it will dissolve caffeine nicely. And then they take the caffeine out of it, and then everything else is still left dissolved in there, take it back in with the next batch, and you keep on going and going and going.
And at which point do they freeze dry it?
And it's probably afterwards, I would have thought, because this is all going on at several hundred degrees centigrade at very high pressures. And then once you've got the caffeine out, you can then put it in all sorts of other things. Things like Coca-Cola's got a load of caffeine in it, Pro Plus tablets, a lot of headache
other
remedies.
Brands exist,
of course, are available.
Why is it that I can't just walk into my coffee store, which could be any coffee store across the country, and get a plain black cup of coffee? Just want coffee and water. I don't want a latte. I don't want an espresso. I don't want a choco mocha waka waka waka. Got one from Bob in Essex here, Dr. Dave.
Okay.
About this? We're going to go on the hop here. When we hear of an average temperature, how long ago was this average temperature recorded? As surely with global warming, these averages would change.
So, yeah, I guess he's thinking about average global temperatures rather than any other average temperature. I think it is actually quite a big issue. Various people do argue over what is the average temperature. So if you're thinking about average temperature over the last 10 years, it's probably 10, 15 years is probably good for a climate range, because the temperature in individual years goes up and down hugely. I'm fairly sure this year, definitely in the UK, is going to be very different to 2 or 3 years ago. So, 5 or 10 years is probably a reasonable thing to be looking at the temperature, how it's changing. When they're looking at how much it's increased, it always depends when you started from. So, sort of 200-300 years ago, we were in a mini ice age, so temperatures went up a lot after that. So if you start off measuring your base temperature at the middle of a mini ice age, then the temperature's going to be looking very hot now. I think mostly when they're thinking about carbon dioxide global warming, they try and look at a period before we were starting injecting a lot of carbon dioxide into the atmosphere. So probably end of the 19th century, when it was only Britain really which was burning lots of coal, definitely before 1950, when the sort of amount we were burning fossil fuels went up hugely. So it is an issue when you start as your base point, but that people try and work around it.
Now we have to ask everyone, Dr. Dave, because I have been asking everyone, but what did you learn today?
Well, I saw quite an interesting story today about mammoths. Mammoths, sort of big things, a bit like hairy elephants, basically, with small ears, wandering around.
I've seen Ice Ages,
okay. Now, occasionally, the Russians find one or two of these buried in a piece of tundra where it's been frozen for the last 20 or 30,000 years. So what some Russians and some American scientists have been doing, digging up these mammoths and then taking their hair out, and then they're trying to get the DNA out of the hair. So, because hair is the best thing to get DNA out of, apparently, because if you go in a bone or something, fungus gets in there, and bacteria get in there, and you end up reading the beautiful DNA of a fungus,
Of other things. Oh,
which is very good. Whereas hair is nice and contained, and if you get the little bit of DNA out of the root, it tends to be quite contained. And if you clean it well, you can actually get pretty much only mammoth DNA out. And so they've been digging up various mammoths and getting DNA out of them, and apparently they've got about 80% of the DNA of a mammoth now. They get it in lots of little chunks because it's been sitting there for 30,000 years. It's a bit damaged, and they sort of line the chunks up on elephant DNA. They reckon they've got 80%, and it's only about 0.6% different from an elephant.
So this is obviously useful to see how the transition from a mammoth to an elephant. And is it possible to date that from this DNA?
Probably wouldn't be dating it from the DNA. You'd probably date it from the carbon in the mammoth, because carbon, when it's out of the atmosphere, slowly decays, and you can work out carbon-14 decays into nitrogen, I think, and you can use that to date how old the mammoth is. But it's really interesting to see. I mean, basically, it's an extinct creature. We don't really know how it worked, and we're getting to look at really in detail how it works. Lots of people would be quite excited if you could make a mammoth from this DNA, which in theory, if you got a perfect bit of mammoth DNA, there's no fundamental reason why we couldn't then sort of put it into an egg and then feed the egg into a female elephant and then see what comes out a couple of years later when the pregnancy is finished.
So that sounds like an arrestable offence to me. I don't know.
You would be cloning an ancient mammoth from 30,000, 40,000 years ago. Unfortunately, they reckon the DNA is probably a bit too damaged for that.
Be quite angry, wouldn't it?
It'd be a bit lonely as well.
Great stuff. We've got a question here is from Alessandro Troiano. That's got to be an Italian name. Can a powerful telescope see back in time?
Fundamentally, yes. All the light which is coming towards us is travelling at the speed of light. It's about 300,000 kilometres every second, which seems incredibly fast, but astronomical distances are far greater than that. So the closest star, the light left it about 4 years ago. The light left the sun about 8 minutes ago. So just the closest star, you're always looking 4 years into the past. If you start going across the galaxy, you're talking hundreds of thousands of years. To the edge of the visible universe is billions of years, probably about 13 billion years or more. The light's been travelling before it gets to us. I think what he was wanting to know was whether we could use this fact to look back in time. So if you could get on a really fast spaceship, fly 50, 60 light years away, and look back in time and see the World War going on, or who shot JFK or whatever. If you had a good enough telescope to be able to see that detailed. The problem is you can't travel in a spaceship faster than the speed of light, because the way the universe works, we don't seem to be able to go faster than the speed of light. So we could never go out and then look into our own personal past. But if some useful alien or random piece of universe happened to set up a big mirror 50 or 60 light years away, and we get a good enough telescope to look at that mirror, and we could see the Earth in that mirror, then we could look back in time.
Don't point it at the sun, though.
Yeah, it wouldn't do a lot of good to your telescope.
Really or your eye, surely.
Yeah, or your eye, yeah.
Anyway, here's another question from Tomislav Belosic, who says, in case we do spot a large extinction event-worthy meteor on a collision course with Earth a couple of years in advance, would there be any way to stop it? And if so, how would we do it? This is asked with a background of we often hear that a statistical chance of dying from a large meteor strike is quite high. In addition, it is said that we would probably have difficulty to actually spot anything that might be approaching us. So,
well, for the first time, someone's actually spotted a meteor before it hit the Earth. This was a few weeks ago, a fairly small one, only a few metres across, and they only got about 2 days warning, so we couldn't possibly do anything about it. It hit the atmosphere somewhere above Somalia, I think, in Africa, and it produced quite a good explosion in the atmosphere, but definitely not big enough to get down to Earth and do any damage. Whether we could do anything about a meteor or an asteroid which is on a collision target with the Earth basically depends on how big it is, because if you get something several kilometres across, then it's going to weigh, every cubic kilometre of rock is going to weigh several billion tonnes, And if you've got something a couple of kilometres across, that's going to be several cubic kilometres of rock. So you're talking billions and billions of tonnes of rock. And we can only send up like 20 tonnes of space rocket into orbit, and then you've got to get it out there.
The differences in there.
So you've got to have to put a really quite efficient motor on that space, on that asteroid to move it out away the Earth. The one thing you have got working for you is the longer in advance you can see it. So if we saw it 20 years in advance and we could predict that it was going to hit the Earth, you've got much longer to deal with it. So you could sit there and push it very gently for years and years and years until it just missed the Earth, and then we'd be all right.
So through the rotation of the Earth, you'll be able to predict where...
Well, from the way the Earth's moving around the Sun and the way the other planets are affecting the gravity on everything's very subtly, and then how fast this asteroid's moving, you'd be able to work out that it was going to hit the Earth several years in advance. I mean, they can definitely predict that things are going to be a near miss sort of 30, 40 years in advance now. One thing which lots of people suggest is sending up a nuclear missile and just trying to blow it into pieces. The problem with that is you then end up with lots and lots of smaller meteorites which are going to hit the Earth anyway, and you can't blow them far enough away to miss completely. So you just end up with lots and lots of impacts, and you're probably not in a much better situation. People have suggested trying to get a big mirror and shine it on one side of the asteroid and keep shining on that side of the asteroid, and then actually light will gently push the asteroid away. So with this big mirror, you could ever so gently push the asteroid. You don't have to push it that far, just a few thousand kilometres over 40 years. And then you might just get it to miss. Otherwise, it's a case of somehow getting some kind of nuclear-powered rocket and gluing it to the asteroid and pushing it away. Of course, the problem is no one really knows what asteroids are made of. And I think the Americans tried to impact one, and they sort of shot something at an asteroid. Definitely maybe a comet, and they suddenly discovered it came out the other side. So, and actually trying to push something which is kind of like a loose, rubbly mess.
Was that NASA?
I think it was NASA. Yeah.
What are they like?
And if you can't actually push it, then you're in trouble, because if it's so kind of squidgy, then so anything kind of actual big rocket is a problem, which is why the light's quite nice, because then you can push everything very gently.
Now on to a question from Andy Leonard. This is a very interesting question, Dr. David. It says, do guns rely on oxygen to work?
The simple answer is no, because basically the definition of an explosive, or for something to be an explosive, and the bullet's fired out by an explosive inside the gun. With normal guns, it's cordite. Basically, that is a substance which both has something which will burn in it, so the traditional explosive with gunpowder, so it would have some sulphur and some charcoal in there. It would also have something which will give out oxygen when you heat it up. So in gunpowder's case, saltpeter, which is sodium nitrate, or potassium nitrate, I think. They used the way they got it.
I often get them confused myself.
I think both will work, you know.
Yeah.
And then basically when you heat that up, it gives off oxygen, and then the carbon in the charcoal and the sulphur can then burn in that oxygen, which makes it hotter, which means you give off even more oxygen, so that more carbon and sulphur can burn, and so it gets hotter and hotter and hotter. It produces lots of gas, which expands and fires a bullet out of the gun. With more modern high explosives, things like TNT, the oxygen is actually in the same molecule as the fuel. So you've got a load of oxygen locked in. It's actually some nitrate sort of groups glued onto the toluene in the middle of it, which means that it can actually burn incredibly quickly. Because if you heat it up, then the oxygen's in exactly the same place as the fuel. So it can burn incredibly quickly and incredibly violently, which you call a high explosive. You actually get a wave of burning called a shock wave going through the explosive as this kind of shock wave. It's like a wave going through it. As this wave meets a new explosive, it's got enough energy to trigger that reaction, and so you get more energy release, which makes the wave stronger and stronger and stronger. And so you get this supersonic shock wave which comes out of the explosive, and it's really, really, really destructive. So because the gun has got the oxygen in the gunpowder to start with, it doesn't need any more oxygen from the air, so it will work underwater or in a vacuum. In fact, the Russians have actually used to build a gun in space. During the height of the Cold War, they were a bit paranoid the Americans would come up and try and steal their space station. So they actually put a 20mm cannon down the middle of their space station. They'd fire it a couple of times, and it worked in space. So, yes, you don't need oxygen for a gun to work.
Crikey. Why does paper become translucent when exposed to oil? This is from Drew Gilmore on the email.
Okay, it works as well with paper, as does clothing, as I expect you've noticed in the past. Basically, what's going on is that white objects, I mean, they don't actually have a colour. All they're doing is taking light in and then bouncing it off in random directions. In fact, I don't know if you ever looked at scratch glass. If you've got glass, it's perfectly transparent.
Yeah, it chips it out, doesn't it?
If you smash some glass, if you look very close to it, you can see sort of images through all the pieces of glass, but everything's distorted because when light hits glass, it slows down, and it's a bit like if you drive a car off into some sand, it kind of bends into it slows in and it bends and it refracts.
I do know what you're talking about.
And so it refracts in all sorts of different directions. So if you look at the glass close up, you see a distorted picture of the view of the world. But if you look at kind of smashed glass from a long way away, it just looks white. So you can just see a mixture of everything, all sorts of bits of the image all over the place, all mixed up, and because all colours are in around you, it all averages together to be white. So paper's white because it's scattering light in all sorts of different directions. Now, if you put oil or water on the paper, the speed of light in oil is much closer to that of the cellulose in the paper. So when the light goes from the oil into the cellulose, it doesn't bend as much, so it tends to carry on fairly straight. So it doesn't get distorted as much, doesn't get scattered as much, so the paper's more transparent. And because the surface of the oil is very flat, the light will go straight through that, approximately straight through the cellulose fibres in the paper and out the other side, so light will go through it much better.
Very good stuff. Matt in St Ives texted in and said, does toast always land butter side down, and does time ever stand still?
Well,
two questions.
Two separate. I'll start on the first one.
Yeah.
Okay. In fact, the toast always landing butter side down is an experiment I've done myself, in fact, in this very studio. Basically, it doesn't always land butter side down, but if you take a piece of toast, or if you take anything, if I take this piece of paper and slowly slide it off the desk, as it slides off, it starts to rotate. And generally, if you push the piece of toast off a table at about the sort of speeds you normally knock it off a table, and the table's about the normal sort of height, on average, it would have turned about the right amount to end up upside down on the floor. If you've got a very, very high table, above about 3 metres, then you'd normally knock it off and it'd land the right way up. Or if you knock it off incredibly quickly, it tends to land the right way up. Or
so we all need slowly to reach at 3 metre high table.
So yeah, if you go for a 3 metre high table,
if you're clumsy in the morning, raise your table, raise your game, keep your toasted sunny side up. So it's about the equation between how high the toast is when it originally starts to rotate off the
Yeah, because if it's higher up, it's got more time to rotate, so it will have turned the whole turn as it falls down, so it will tend to land the right way up.
And does time ever stand still? The batteries stop, I guess.
I think your perception of time does change really radically as things go on. I mean, the most obvious thing is when you go to sleep, your perception of time, it's as if an instant's gone past. You can sometimes you just shut your eyes and then you open them again and it's light. So your perception of time is very, very strange. If something very exciting is going on, you feel like it goes quicker. But if you look back if you have a day with lots of exciting things, it suddenly rushes past because it feels like lots of things happening. If you look over it, but if you look over it at the end of the day, it seems like it was a long day. Whereas if you've got nothing happening, it feels like it drags on for ages. But at the end of the day, it feels like it's just gone like an instant because you can't remember anything interesting. So definitely when you look back over things, it seems that how long it takes, it seems to do with how many interesting things you can remember, because then you're kind of measuring time by how much has happened.
Is it true that dreams in real time only take about 2 or 3 seconds?
I think certainly the periods of you can have dreams which seem like they've gone for hours and hours and hours, but definitely they only normally go on for a few minutes. And the other thing is that if you have something really scary happen to you, this happened once when I went down a death slide and it all went horribly wrong. Your brain sort of has some kind of incredibly fast mode whereby you've got more time, so it can sort of think about what's going on a lot more, and so possibly if something's going to kill you, you've got more time to think about getting out of the way. So it seems like time goes incredibly slowly when something really scary, really dangerous is happening to you. So your perception of time can change hugely, but time itself, it seems to be going at the same speed all the time.
Now, we've got a question here saying, why do diet fizzy drinks stay fizzy longer once opened, but regular drink goes flat in no time at all? From Mark the Storman. Thank you, Mark.
I don't have any definite evidence on this. I do know that if you take mints and throw them in a diet drink, they tend to produce more foam and produce a better fountain. If you've never seen this, you put some mints in a bottle of Coke, or in fact any old lemonade or whatever. In fact, you can just chuck sand in as well. They take little bubbles down with them, and these bubbles can grow, and you get lots of bubbles, lots of foam creating very quickly, and you get a wonderful fountain out the top.
Does it have to be neat Coke, or can it have a...
It works best if it's still in the bottle, because if you've poured it out, quite a lot of the fizzes escape. Okay. But if you get if you add a pint of Coke and pour a spoonful of sugar, works lovely. A spoonful of salt will be more unpleasant. You've got little bubbles. Normally the bubbles can't escape, because bubbles can only escape around the edges when you've got something for them to start on. But if you take lots of bubbles down there to start with, all of those small bubbles can grow and create more and more bubbles, and you just get a load of foam very quickly.
I got a text or a call from Giles here saying, how do you get a hard-boiled egg into a bottle without breaking it?
I certainly know how to get a peeled hard-boiled egg into a bottle, because a hard-boiled egg is quite flexible. If you take a bottle with a neck, which can be sort of maybe 2/3 of the diameter of the egg, if you chuck a lit match in and then take the peeled hard-boiled egg, put it over the top and put it in the neck of the bottle, the air inside the bottle is going to get hot, so it's going to expand and escape past the egg. Then at some point the match is going to run out of oxygen, it's going to go out. And then the air is going to slowly cool down. When air cools down, it shrinks, pressure drops down, so because no air can get back in because the egg's making a good seal. Then the air pressure on the outside is bigger than the air pressure inside, so the air pressure will push that egg in through the neck of the bottle. You have an egg in a bottle.
Very clever. What do you want to do with it afterwards? I don't know. What, throw it away? Take it down the bottom bank?
Improve your... show off to your friends. Or the real trick is how to get it back out again.
That's it for this week. Thanks for listening. Remember, you can send The Naked Scientists your questions by email. chris@thenakedscientists.com is the address to write to. And if you want to find out more about The Naked Scientists, then drop by our website, nakedscientists.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.